some factorial thing from, you know, and in this case, the gamma function goes all the way up to 2 plus alpha up to 2 plus 7 alpha. So follow this and also follow the derivation. The derivation is in separate pages I have sent, and then follow how this problem is solved. Now, you will notice a difference between, because I'm not going to talk about furrow irrigation systems. I'm not going to talk about border strip irrigation systems because the principle is the same. But you will notice a difference between how now we talk about how we calculate Y, you will see a difference on how we calculate Y in furrow irrigation systems, and even how we calculate X in furrow irrigation systems, because now that in that case, it is much simplified. It is more of a one-directional flow. Now, what is again important when we are dealing with border strip irrigation systems is, if this is your border, and you release your water in this point, at some particular point, you are going to get the water advancing, and then you are going to cut down the water inflow, and then the remaining water which was accumulated on the surface will continue to flow downstream. And then for border strip irrigation systems, you have a collection system at the bottom, at the downstream part of the border. So you are going to have some water flowing and leaving the system. And at the same time, again, for check basins, you do not have a collection system. But now furrows are smaller. So you are going to have a very thin kind of, just very, very many furrows. So generally this is the case. And what happens, because now you also have to understand what we call the recession flow, and you need to work with also what we call recession curves. And when you are studying the recession curves, you look at them together with the advanced curve that we have seen just previously. So on the one hand, you have an advanced curve, and from the advanced curve, we also want to know what is the recession curve, because effective or maximum infiltration of the water occurs during the period between the advanced curve and the recession curves. And I want to explain this advanced curve. So recession curve. So we have seen the advanced curve. It gives you the distance the water has traveled with time. Then we have a recession curve. A recession curve is on surface. So let me try to explain it. So after you have cut off the stream of water, so at some point you have released your water and it has gotten to, let's say, 8 out of 10 of the distance, or 6 out of 10 of the distance, 0.6, 2/3 of the distance of the length of the border strip. And then you cut your stream. What will happen? Water that has been detained, accumulated on the surface, will start now to disappear. Remember, water flows due to momentum, due to energy that water possesses. And for it to continue flowing from this top part, you have to have more energy driving the water. And where was that energy coming from? It was coming from, of course, mass balance and energy, and it was coming from the inflow of water, which is released into the border strip. But you cut it, what happens? The water at this point now is going to, because infiltration is still happening, so it is going to infiltrate. So at some point, you start At some time, you started to release the water, and then the water starts to move downstream. And at some point, so many minutes after, of course, this time is of course derived from, it is derived from infiltration equations. You have run an equation and you have been able to determine after so much time the water will fall at this, and the infiltration capacity at this point is going to be so much. So after some time, elapsed time, you cut off your stream. The time you started irrigating and the time you have cut your stream, that time we call it time of ponding. And water is now going to start disappearing from the ground again. So in the advanced stream, water started accumulating on top of the surface and traveling downstream. On the recession curve, water will start disappearing from the ground surface, and also that effect is the upstream part. Just a little while later, you're going to get water disappearing downstream until at the end of the water at all on the ground surface. If you get normally when you plot the recession curves and the advance curves, you see a general parallel profile difference between the two. And what this tells us is we have kind of uniform distribution of water throughout the border. So if you do your experiment and then you do not have this kind of uniform kind of a profile, then chances are that you did not have uniform flow in your border irrigation, uniform irrigation or uniform distribution of water in your border strip. Now, we have what we call infiltration of opportunity time. That is time of ponding. This is this time. And why is it critical? This is when we have infiltration capacity occurring at a rate equal to the maximum or ultimate infiltration capacity of the soil. That is when we have ponding, above the ground level. It is the time between advanced time and recession time. And it is constant, it has to be constant throughout the distance of flow. Now, once you have those characteristics, you have advanced time, you have recession, you have advanced curve, recession curve, you have the infiltration capacity. How do we design the border strip irrigation systems? And there are protocols on how to go about it. Number one is to determine the length, width, and slope of the border strip. Secondly, you determine the depth of water required to replenish the soil moisture in the root zone. And how do you determine the length, width, slope of the border strip? And when you're looking at what did I say? When we're looking at the various irrigation systems, the theoretical part of it, we have typical layouts, typical dimensions that you can use for border strip, and that is usually dependent on a number of things. The types of soil, and also the heterogeneity, the distribution of the soils in the area. We want to have a border strip that covers, that is found or that is been developed in an area where we have kind of uniform soil characteristics. Again, we're also talking about the slope. We're also talking about the crops. We're also talking about, there are so many factors to consider when selecting or, when sizing these border strips. And those are factors we can find in engineering, irrigation and engineering 1. So first, you determine the length, wind, slope of the border strip. Then 2, you determine the depth of water required to replenish the soil moisture in the root zone. Of course, what do you do? Number 1, you have to know principles of irrigation, of crop water requirement, irrigation water requirement. You want to determine the depth of water. You want to determine, do you want to irrigate up to field capacity? We know all these things, how to determine the depth of irrigation or the crop water requirement, the irrigation water requirement specifically. Actually, it is more of the irrigation water requirement than the crop water requirement. So that is how you do number 2. Number 3, you you determine accumulated infiltration time relationship of the soil under existing soil conditions and vegetation cover. So essentially, run an infiltration equation. Mean Y. Run an infiltration equation to run Y. And you can already do an experiment, or you can do an experiment, or you can use pre-existing conditions. You estimate hydraulic resistance, Manning's N, based on the roughness of the soil. Then next, you determine the average depth of flow. Determine the average depth of flow. Where is this average depth of flow I'm talking about? I go back to this profile. So essentially, we are just trying to determine these things. So we determined the length of the length and the slope. We determined the depth of water required to be, so that you can replenish the root zone, and that is going to be the Y. It is not going to be the Y. The Y is the infiltration time relationship. You can get the Y from the infiltration time relationship, but the Y has to be related. It has to be related to the depth of water required to be irrigated into the ground, so that in the downstream part, the amount of infiltration that is going to the distance, the infiltration depth that will have happened at the end of your stream, at the end of your border strip, is going to be, it is going to be at least equal to the depth of irrigation that is required. And then I've said you also determine the desired infiltration opportunity time, the opportunity time, that is the time between the advance and recession curve, and you determine hydraulic resistance, then average depth of flow. The average depth of flow is the dx. Average depth of flow is the dx. And you assume a constant. Why? You can see there is very little change in if you have a gentle, very nicely gentle slope, you are going to have almost parallel, the water surface slope being almost parallel to the ground level. Remember, when we are doing border strip irrigation systems, and even most of these surface irrigation systems, leveling is one of the key things that we need to do. So the average depth is estimated. And then next, we are supposed to determine the water front advance is predicted. That is the value X in that profile that I've just left. And finally, you estimate the Finally, after you have determined those variables, now you design your irrigation system for optimum water application efficiency and border length. Now, how do you do this? How do you do this? First of all, what you do is to calculate this waterfront advance kind of calculations. You make like a family of curves given different streams. You do that experimentally, or you already have some literature kind of curves somewhere. So you have to develop them first, so that now if you have a certain stream, you see if you have different streams, like this one is lowest flow, higher, and then highest. So if your stream or the stream that you plan to apply does not lie neither, you already can see, you can easily interpolate between these curves. So the total volume of water admitted in the border stream per unit width is usually equal to the intra stream size multiplied by the length of time the water flows into the border strip. We have already seen that before. And for a preliminary design, you can suppose that the period, that time that you apply and multiply with Q is equal to the time required for the advance front to reach the end of the border. That is when X is equals to L, when this X is equals to the entire length of the border strip. So that if you were then to calculate the total volume of water applied, it will be equal to Q times T. It is going to be Q times T. And once you're given this, you can now determine the minimum volume of water V, minimum amount of volume of water per unit width of border required to apply, at least Y centimeters corresponding to T opportunity time over the entire length. That is VR is equals to Y times L. And then the volume of water admitted must be equal to the volume required by the cell. Therefore, what we have calculated here should be equal to Y times L. Of course, I think I have already explained that. I had explained that just before in that image. I said the Y infiltrated water must be equal to the water required to replenish the root zone, and that is what we have here, just equating the two. And once you have now that, because this is kind of a continuity equation, this is just basically a continuity equation. Secondly, you can calculate a volume balance function, a volume balance function. Again, it is a different form of a continuity equation. What here we are saying in this kind of, is it conservation of mass or continuity? Both continuity and conservation of mass are the same. So here we are saying The amount of water that you release should be equal to the water in the minimum list should be equal to the water that is required to replenish the root zone. And then secondly, we are saying you can also have a second volume balance function, which is a function of the discharge, opportunity time, infiltration opportunity time, the depth of infiltration, and length of the border strip. And you can develop such kind of a volume balance function B, and we have so many volume, like here we have very many volume balance functions that have been developed for specific cases. And it expresses the difference between the volume and the volume of water admitted, where is it? Yeah, this one. The volume of water admitted to the border strip per unit width. And VR, what is VR? VR is the minimum amount of water. VR is the minimum amount of water per unit width of border strip required to apply a depth of at least y centimeters corresponding to an T infiltration time. Then you have the Y naught. In this case, you are presuming a uniform depth Y naught corresponding to an opportunity time T. So what this volume balance function assumes, what we assume in this volume balance function is that at the end of the infiltration, we are going to have a uniform infiltration equal to Y naught, but we know that one is not true. At the end of the day, we are always going to have a profile that is like this, but this is the assumption that the infiltrated water is constant throughout, the length of the border strip. Again, when you come to, by definition, therefore, the volume balance function, can easily be written as, it is still again a water balance kind of a thing. It is written in this format, by taking into consideration the volume applied and volume infiltrated. And therefore, the balance function is equals to total water applied minus total water infiltrated. And what you see with this volume balance function, it is trying to minimize. It is trying to minimize the loss of water. Now, when you look at the equation 10, again, volume applied should, in the very least, equal to the amount of water infiltrated. So that means we have very little water that is being collected in the drainage channel. So what the equation 10 and equation 810 and 811 are doing is to try and minimize the amount of water lost through drainage. So what you do, you construct B, the function B, for each possible and probable field lengths. For example, for 60 meters, for 50 meters, for 40 meters, for 30 meters, and what have you. And this is a volume balance function calculated from this. And in the horizontal axis, you have an accumulated infiltration at the upstream end of the border in centimeters. Basically, this is the D naught. So first of all, you plot the volume balance functions B. These are the lines, the diagonal lines flowing, the diagonal lines, the ones that I've just indicated here. I don't know, it is northwest to southeast. And then you also need this other set of lines, the BD. And what is the BD? The BD is